It turns out that at room temperature, do all ammonia molecules and water molecules move at the exact same speed? Would you predict that everybody's moving at exactly the same speed? No, at room temperature, the ammonia molecules and the water molecules could be moving at different speeds. What about all the water molecules alone? All the water molecules, do they move exactly at the same speed? At room temperature. So if I could actually watch a water molecule and compare it to the other water molecules, they're behaving exactly the same, exact same speed, exact same energy? No, it's not the case. In fact, if I were to look at it, I'd see a whole bunch of different speeds. Different. And in fact, that's what we call a kinetic energy distribution. The kinetic energy distribution is going to plot two things. On the left axis is going to plot the population. On the right, or the bottom axis, we're going to plot the kinetic energy. Okay, this is going to be at room temperature. If we have a kinetic energy distribution at room temperature, we'll see that the entire population isn't moving exactly the same. They're going to be slow molecules, and they're going to be fast molecules. But most of the molecules are going to be moving at some speed, or some energy around the average here, which is around here. But there's going to be a fraction of molecules that are way below average and a fraction of molecules that are way above average in terms of kinetic energy. And it's this fraction that's way above average that we are concerned with. There's going to be a certain cutoff in energy here. If we go beyond this energy cutoff here, then there's enough energy to react. Even though this is an unfavorable reaction, that collision could be quite violent, causing ammonium and hydroxide to form. If I had a billion water molecules, let's say a billion, if I had a billion, then over here I would only have about 4 molecules with enough energy. And so out of a billion population, about 4 have enough to react. Actually more than 4, but 4 will be successful, let's say. And so in this particular diagram, even though there's no driving force, there's no driving force in the forward direction, there is a tiny bit of reaction that occurs, and that tiny bit of reaction that occurs is due to collisions, having energetic enough collisions here. It's high energy too. Situation is this. Once I make these, ammonium and hydroxide, that's a very unstable, very reactive combination. Ammonium's an okay base, ammonium is an okay acid, hydroxide's a strong base. These two are going to react immediately to form ammonia and water. And so as soon as I form this stuff, it's very likely that these two will react to revert back to ammonia and water. But the situation is this. As soon as I form this, and this reacts and reverts back, what happens next? What happens next is there's another violent collision. Can you stop the ammonia and water from colliding? Is it possible to stop ammonia and water from colliding? No. Like if I'm looking at the water here, can I tell them to stop colliding with one another and just behave? No, you can't, because they're going to collide. And some of them are going to collide with quite a bit of energy, because some of them, small population of them, have quite a bit of energy to react. And so the situation is like this. We set up a dynamic equilibrium. It's a dynamic equilibrium because what happens is we're going to form these, but as soon as we form these react. And so what we're going to do is we're going to create a stable concentration. One way of thinking about this is if I have a ball pit. If I have a ball pit like this, and they aren't moving, then all the balls are going to settle to the bottom of the pit. However, if I start giving it kinetic energy, and there's a ramp here, then some of the balls can roll up the ramp. But is that stable if the balls roll up the ramp? No, but some of them will, because you're shaking this, and some of these balls will have enough energy to roll up. But what's going to happen? Well, they roll up. They're not stable there. They got to roll back down. And so we're going to reach a point where we'll hit a dynamic equilibrium. That is, the number of balls that roll up is equal to the number of balls that roll down. So eventually you reach a steady state, a state of equilibrium. And that state of equilibrium could be like 4 balls on the ramp at all times, you know, something like that. Well, this is the same thing. We'll produce this product, but we'll immediately consume it. So we're just going in circles, and eventually we're going to hit a state of dynamic equilibrium. And in that state of dynamic equilibrium, we're going to have 99.9% this and about 0.1% this. And that's going to be stable. It's stable, you know, we're going to have about 0.1. Actually, it's less than 0.1, but we'll have about 0.1% this, 99.9% this. But what's happening is it's constantly reacting. You know, it's constantly being formed and consumed. And so since we're going in circles, we're going to build up a stable state. It's not going to be 50-50 in this particular case. It's much more favorable to have these. So that's why it's greater than 99.9% this, less than 0.1% this. And so that's it. It depends on how steep this ramp is and how tall it is. You know, the steeper it is, you know, the higher energy you got to climb. Taller it is, the more. And so, you know, it's really going to favor the balls here. But if this were not so steep and not so tall, then maybe be bigger balance, you know, better balance between the two sides. So this is the dynamic equilibrium, and this is what we call partial reaction. Well, you know, it's so little reaction. You know, 4 out of a billion doesn't seem like that much. But this makes a big impact. What 2 things, you know, this partial reaction will have an impact, direct impact on 2 things immediately, let's say. This partial reaction, even though it's not much, it's like 0.1% reaction, let's say, or less than 0.1% reaction. One thing it's going to do is it's going to impact the pH. The pH is how acidic or how basic the water is. This reaction generates some hydroxide, and that hydroxide changes the pH of water. And so this will have a direct impact on the pH. Two, for this specific reaction, what happens here is this. We form some ions from the molecular compound. Those ions can participate in metathesis reactions. And so this is what we had in the lab. We had something like iron 3 chloride, is that correct? Iron 3 chloride plus ammonia. When you look at that reaction, does that look like a double replacement, AB plus CD type? What kind of reaction does that look like to you? Okay, A, what is A? A is iron 3. B, chloride. What's C in D? Well, CD, well, ammonia is what we call a molecular compound. CD should be an ionic compound, so it doesn't fit that. But when I look at this, this is a metathesis reaction. Indeed, it is a metathesis reaction. This is actually a metathesis. Because what's happening in this particular reaction is this. You know, what were metathesis reactions again? Metathesis reactions were favorable ion combinations. Well, ammonia is not an ion. And so what is the favorable ion combination? The favorable ion combination is this. It's FeCl3 plus ammonia. But it's not just ammonia, it's ammonia and water. When ammonia and water come together, then a small population of those can collide violently to produce ammonium ions and hydroxide ions. And so when I see ammonia and water, I imagine the small population of ammonium hydroxide that's produced from some of those violent collisions. Now let's look at this. If I do iron 3 chloride as my AB and then ammonium hydroxide as my CD, then it's easier to predict. What am I going to form for this? AB plus CD yields yeah, AD. What is AD? A is iron 3, D is hydroxide. So AD is iron 3 hydroxide. What is the formula for iron 3 hydroxide? FeOH3. Now, iron 3 hydroxide, is that soluble or insoluble? Hydroxides are insoluble, except for group 1, ammonium, calcium, strontium, barium. So this turns out to be not one of the exceptions. This is insoluble, so it's going to precipitate. This is solid. Well, we have driving force. Driving force right now is precipitation, looks like. AD plus, what's the other product? CB. C is ammonium, B is chloride. So we're going to produce ammonium chloride. What's the formula for ammonium chloride? Well, NH4Cl. Ammonium salts are all soluble, so that's going to be aqueous. And so we have a driving force for this. It's precipitation. So I should balance it. The easiest way to balance it is by balancing it by ammonium hydroxide here. Here I have one iron, one iron. I have 3 hydroxides here. I only have 1 hydroxide here, so I'm going to bump this up to 3 ammonium hydroxides. That gives me 3 ammoniums, which I'll put over here as 3 ammonium chlorides, and then 3 chlorides, 3 chlorides. So it's balanced. In order to form 3 ammonium hydroxides, I need 3 ammonias to collide with 3 waters. Each ammonia colliding with each water just yields 1 ammonium hydroxide. To get 3 of them, I need 3 each. Now brings us to a point. How should I write the CE for this? For the CE, should I write it as ammonium hydroxide or should I write it as ammonia and water? It's going to be FeCl3. Should I write ammonium hydroxide or should I write ammonia and water? You will get some debate about this particular topic because what reacts? What's reacting is the ammonium hydroxide reacting. In fact, the hydroxide is reacting. And so some people will say, write it with ammonium hydroxide, but I don't. I say write it with ammonia and water. And so the way I write the CE is this, FeCl3 plus 3 ammonias plus 3 waters. Now, the reason I do it this way is this. If you're to go to the store to buy some ammonium hydroxide, because ammonium hydroxide is what's reacting here, you're going to be disappointed potentially. Because if you go to the store and say, okay, I'd like to buy some ammonium hydroxide, you know what they're going to give you? They're going to give you 99.9% ammonia and water and less than 0.1% ammonium chloride. And then you go, I paid for ammonium hydroxide, sorry. I paid for ammonium hydroxide and I'm getting less than 0.1% ammonium hydroxide. I'm being ripped off here. Are you being ripped off? I'm thinking, so you return it. You return it and they replace it with another batch of ammonium hydroxide, and what is it? It's the same thing. You get 0.1% ammonium hydroxide, 99.9% ammonia and water. Why? Why? It's because, the chemical reaction there, the ammonia and water, the driving force is back. So even if they gave you 100% ammonium hydroxide,
it's going to react to form ammonia and water, and eventually we're going to have this balance. There are going to be some molecules that can go uphill to form ammonium and hydroxide because it's not so stable, but it's not a huge number. And so, in other words, if you're going to buy these chemicals, you're going to buy ammonia and water. You're not going to buy ammonium hydroxide. You're not going to be able to buy that, right? Because it's not stable. There's a driving force for reaction. Ammonium reacts with hydroxide to go from stronger acid, stronger base, to weaker acid, weaker base. It's driving force for that. But that's not to say we can't have a little bit of partial reaction, and that's the little bit of partial reaction is what we're counting on for this metathesis reaction. This is not a traditional metathesis setup, but it is a metathesis reaction. Whenever we have aqueous ammonia, it's metathesis, potentially, as well as acid base. Okay, and then it's going to form iron 3 hydroxide solid plus 3 ammonium chlorides, and the driving force is precipitation of iron 3 hydroxide. That's the CE. Let's go to the IE for this. The IE, do we ionize FeCl3? Ionize or leave it alone? Ionize. Into what? Fe3 plus 3Cl minus. Okay, that's good. We didn't lose any atoms, so we're good. Ammonia, ionize or leave it alone? We leave it. That's correct. So that's going to be 3 ammonias. Water, do we ionize it or leave it alone? Is water a strong acid? No. Is water a strong base? No. Is water a soluble salt? No. And therefore, yeah, leave it alone. Iron 3 hydroxide, ionize it or leave it alone? We leave it. It's an insoluble salt, not a soluble salt. So leave it. Ammonium chloride, ionize it or leave it? Ionize. It's going to ionize into 3 ammoniums and 3 chlorides. Okay, we didn't lose any atoms there. Let's go on to the NIE. Okay, any spectators? The chloride's the spectator. In fact, it's only the chloride. Fe3 plus 3 ammonias plus 3 waters yields FeOH3 solid plus 3 ammoniums. Let's check the balance. 1 iron, 3 nitrogens, 3 nitrogens, 9 plus 6, 15 hydrogens, 3 plus 12 is 15 hydrogens, 3 oxygens, 1 times 3 is 3 oxygens. So the atoms are balanced, then we check the charge balance. Plus 3 on the left, and then 3 times plus 1 gives us plus 3 on the right. So it looks good. That would be it. So there's one impact of partial reaction. We may not have expected precipitate of iron 3 hydroxide had we not had this partial acid-base reaction occur. Okay, let's stop here.